In rotational motion, we have sum of forces equals ma that can be applied, but remember that we have two types of accelerations, a centripetal and a tangential, and you can see that the centripetal acceleration is directed on the radius of the circle, and the tangential is tangent to that circle, and they are perpendicular with respect to each other. Now, a centripetal has a formula. It is defined by v squared over r, where v is the instantaneous speed and r is the radius of the circle, or the radius of the curvature of the circle. Now we have three formulas, s, vt, and at, where s is the dimension of the arc. Okay, it's measured in meter. R is the radius, theta is the angle, and they are related as follow in the formula. And you'll understand it better with the formula of the pizza. I call it pizza formula. So assume you have an ant moving, or any particle moving from A to B. The distance is s. It is proportional to the radius or to the angle theta. At the same time, it is proportional to the angle and to the radius. Okay, where the units are meters for S and R, and the angle theta is in radians. So in case you want to increase your portion, your pizza portion, you have to increase whether the radius of the pizza or the angle of your part. Some forces can be directed on the radius direction or on the tangential direction, and each force can be projected whether on AC or AT. So we don't have X and Y axis here. In rotation, we have a centripetal and a tangential. Now, to understand better a centripetal, imagine that if AC at 8 meters per second squared is max for a bus to make the curve for a radius r on a road, so what would be the speed if the radius is 100 meters? You can find v around 28 meters per second, so you cannot surpass 100 kilometers per hour. If so, the A centripetal would be more than 8 meters per second squared, and people in the bus would fall, or maybe the bus would fall from its direction. Okay, it would fall down. Now we have four forces at equilibrium acting on the system. We have the hanging mass applying a tension. We have the spring applying another tension on the horizontal direction. Then on the vertical direction, we have the tension too and the weight. If we remove the hanging mass, okay, now we have only three forces and the two tensions, one vertical, one horizontal, and the other weight, okay, weight of the system. So in this case, weight and tension 2 would be 0, balancing each other, and the only force acting on the acceleration, centripetal acceleration, would be F centripetal, which is the tension 3. Okay, in our problem, we have three forces, T3, T2, and the weight. So remember the system. T3 is F centripetal, and it is directed along A centripetal. Now T2 and the weight balance each other, and the summation of them is 0 on the perpendicular direction to AC. It's not the A tangential. So anyway, we don't have an acceleration on the tangential direction, nor on weight or T2 direction. The only projection that we have to do is on A centripetal. So sum of forces equal MA factor can be projected on AC, not AT, okay? So the only force present here is T3, which is the F centripetal. Thus, you can find F centripetal in terms of the other parameters. Now, if you replace A centripetal by V squared over R, you can also replace V by R theta prime from the pizza formula. And theta prime is the angular frequency also, so it is equals to 2 pi over big T. T is the period. And thus you can represent R as a variable with respect to the period of time as a variable. You put r on the y-axis and t squared on the x-axis. The slope would be fc over 4 pi squared m of the system. Remember, from the equilibrium, F centripetal is equal to the weight of the hanging mass. And from the rotation, we know that F centripetal is equal to the tension in the third row.